Alright, in this video we're going to talk about what a hypothesis test is for one proportion. So first I want to kind of talk about what this hypothesis test is. And basically in a nutshell, a hypothesis test is that we are given a true thought to be proportion, right? So it's some proportion that we thought to be true, and we don't know why it's true. Somebody just said it was, or it's just been true. We just always thought it was true for some reason. And we want to see if it's still true. Now, we want to investigate one of three different options. We want to see, did the true proportion get greater than some given value? Did the true proportion get less than some given value? Or maybe we don't really care if it got higher or lower. We just care that it's something different, that it's not equal to whatever we thought it was. So think of a hypothesis test as kind of like a trial. We're putting a proportion that we thought to be true on trial. And we want to see if that true proportion has gotten higher, gotten lower, or has simply changed. And like I said, it's sort of like putting a man on trial for a crime. And when you put that man on trial, you've probably heard this before in maybe government class, you always assume that that person is innocent until proven guilty. So it's the same thing with proportion. So if we were given a true proportion, we want to assume that proportion is still true. We want to assume it's still true, and we're going to excuse me, we're going to try to gather evidence to show otherwise. So it's just like a trial in the sense that we assume the true proportion is still true, and we're trying to gather evidence to show that it is either changed, higher, lower, or simply just changed. Or maybe we find out at the end of the trial that it's not changed at all. Again, just like at a court hearing, maybe you find out that the person at the very end of the trial is simply innocent still, or not guilty, meaning that there was not enough evidence to show that they were guilty. And that's kind of the result. Is usually at the end of a trial we find out that somebody is guilty, or we find out that somebody is, well, we don't maybe know that they're 100% innocent, but we simply just don't have enough evidence to say that they are guilty. And that's usually how it goes. So let's talk about the 4 steps to a hypothesis test. There are 4 distinct steps, kind of like for a confidence interval. There's 3 distinct steps. For a hypothesis test, there are 4. The first one is creating your hypotheses. And the first one we have is we write H with a little sub-zero here. This is known as the null hypothesis. And the null hypothesis is basically stating that innocence, is that the true proportion is still equal to whatever we thought it was true. The true proportion has not changed, so the true proportion is still, well, true. And then we have an alternative hypothesis. We use a little H sub A, so this is the alternative hypothesis. Oh boy. I started to spell that wrong. Hypothesis. And the alternative hypothesis is, again, one of 3 options. It's that the true proportion has gotten greater than whatever it previously was, the true proportion is lower than whatever it previously was, or the true proportion is simply something different than whatever it previously was. And how do you know which one of these 3 options it is for the alternative? Well, you kind of have to base it on how the question is worded, and we'll talk about that when we look at 2 examples. For the conditions, the good news is that we've seen these conditions before. These are nothing new. When we gather the evidence we gather is, of course, a sample, right? So that sample needs to be a random sample. That sample size must be less than 10% of the population, and we've talked about that one before to make sure that we have independence. And the third condition is that we must be a big enough sample. And remember, big enough is 10 or more of those successes and those failures. So again, we need those conditions because we want to use the normal model. Obviously, we're working with sampling, distributions, and sample sizes, and proportions, and obviously the normal model is going to come into play here. In order to do the normal model, we need those conditions to be true. Next is going to be the mechanics and the work, and when we do an example, I will show you exactly how the mechanics are, but the whole purpose of your work, the whole purpose of showing your work is to generate what we call a p-value. So your work creates a p-value. And this p-value is extremely important. And I want to explain, as we find it in an example, I want to explain exactly what the p-value is. It's really important that you understand what a p-value is. And this p is for probability, not for proportion. So don't get it confused with the true proportion p or the sample proportion p hat. And finally, we have our conclusion. We usually have one of 2 conclusions. We're going to reject the null hypothesis, And when we do that, basically what we're doing with this conclusion is we are rejecting the null hypothesis that the true proportion that we thought was true is wrong, and we're going to go with the alternative. So reject the null hypothesis, go with the alternative. Okay? And the second option for the conclusion, again, it's all based on your work here, I'm going to teach you all this in an example, is to fail to reject. Fail to reject the null. And this just means that there's not enough evidence to claim the alternative is true. So we're not going to go with the alternative. We're going to keep the null. Now, this first one, when we reject the null hypothesis, that does not mean that we necessarily accept the alternative. We just have enough evidence to go against the null and go with the alternative. And when we fail to reject the null, that does not mean we put the null on a pedestal like it is the truth that we should all bow down to, but it means that we just simply don't have enough evidence to go with the alternative. So it's like, the guy, Casey Anthony, right, on her trial. If you guys remember Casey Anthony, I mean, I'm pretty sure everybody thought she was guilty, but there just wasn't enough evidence to claim she was guilty. So we just had to stick with the original assumption that she was innocent, even though a lot of people disagree with that. So here's our first example, and excuse me, we'll show all 3 steps here, and I apologize ahead of time for all the typos I'm sure they're going to have here. All right, it is known that it is known that 74% of Americans wear their seatbelt. After a campaign hoping to increase awareness and increase the percentage of those that wear seatbelts, a sample of 205 random Americans showed 164 that wear their seatbelts. Has the campaign worked? So let's go ahead and show our work here. The first step we're going to need is the hypotheses. And hypotheses, ES there for plural. And the first is the null hypothesis. The null hypothesis says, well, we were told that 74% of Americans wear their seatbelts, so we have to assume that that is still true. So we're going to assume that the true proportion is still 74%. So that's the null. And again, the null, a couple hints about the null. It always uses an equal sign, always, and it always uses p. It's always talking about the truth. It's never talking about p hat, some sample. And the alternative hypothesis would be that the true proportion is, we got to read the problem here, definitely use the word increase here. So we definitely were looking to increase the percentage of those that wear their seatbelt. So we want to see if the true proportion is actually higher than 0.74. So I'm not going to write all the conditions out, but we're just going to run through them real quick. The 205 needs to be random sample, okay, and it did say that, so that's a good thing, so we could check that off. The 205 has to be less than 10% of all Americans, and there's a lot of Americans out there. I'm pretty sure 205 is less than 10% of them, and we also need to have that 10 or more successes and failures. So our sample did show 164 successes, and if I do some quick subtraction here, that would be 41 failures. So both of those are greater than 10. So our conditions are checked for the normal model. Now for our work, okay? And for the mechanics. Remember, the mechanics is all trying to find this p-value. So let me kind of walk you through what we need here. The first thing we need is the idea that we know the truth is 74%. And we, again, just like a trial, we have to assume that this is still true. So now that we kind of know the truth, we can create a standard deviation for for a sampling distribution. And the reason why I'm calling this standard deviation, not standard error, is because, again, it's based on some truth, not some estimate. So we're going to go ahead here and do the math here. And we're going to get the square roots. Let's see here. Square root of 0.74 times 0.26 divided by 205. And we get 0.0306. 0.0306. So again, kind of, think about the sampling distribution that we talked about. And remember, a sampling distribution represents what many samples of size 205 could look like. And we would certainly expect every sample to be the truth, 0.74 right in the middle. But we can go up 1, 2, 3, down 1, 2, 3 standard deviations, right, which is 0.0306. So it would not be weird. I'm just going to round that to 0.03. It would not be weird for a sample to come back at 0.77, 0.8 0.8 is when samples would start being weird, or we can go down to 0.71. That would not be a weird sample at all. Don't go down to 0.68. Maybe after 0.68, samples would be a little bit low, a little bit oddly low. So anyway, what we really want to do is we want to think about what our sample showed. Our sample showed 164 out of 205 people that wear their seatbelt. Now, that is 80%. So the trick here, our thought process here is 80% weird, right? Is seeing this sample weird or not? If it's not weird, then you know what? The 74% is still true. If it is weird, but we saw it, it happened, then maybe something really is going on here and we really have changed the percentage of people that wear their seatbelt. So of course I want to see where does the 80% fall. Now obviously based on rounding it to 3%, we kind of know pretty much where it falls, about +2 standard deviations, but let's actually go and calculate the z-score because you will need an exact value. So it's the observed statistic. Remember, this is the observed statistic. This is what we observed, was be 0.8 minus what we were hoping to see, the expected mean, 0.74, divided by 0.0306, our standard deviation. So when I do that, I of course get 0.06 on top. I'm going to divide that 0.0306 on the bottom, and I get a z-score of 1.9608. Now store that on your calculator. You're probably going to want to keep that number. Now, we want to find, so again, that falls about right here, right? I mean, 1.96 is, we were rounding, but pretty close to 2 standard deviations. Now, that should already be giving us a heads up that we've talked about 2 standard deviations or higher as being kind of weird. But we want to actually find the p-value. And the p-value, and I'll explain really, really closely what it is, the p-value is the probability of being at the observed statistic or more extreme. So in our case, or higher. So we are going to go ahead and use a normal CDF on our calculator here. We're going to go from the 1.9608 to 99 because we want to look more extreme. So when we grab that, we get a z-score, or a p-value, a p-value of 0.0250, really, okay? So about 2.5%, okay? And this is a really important number. I mean, all of our work is based on trying to get that number. So let me explain one more time what a p-value is. It's the probability of seeing our observed value of 80% or more extreme. So what we're trying to say is seeing 80% of people wearing their seatbelts or higher occurs 2.5% of the time, or occurs in 2.5% of samples. Now, all of this is, of course, assuming that the truth was 74%. So a final nice answer for what a p-value is, it says if the null is true. If the null hypothesis of 74% is true, the chance of seeing 80% or higher occurs 2.5% of the time. Now, this is the tricky part, right? This is where our conclusion comes in. Do we think that that is rare? Yes or no? Well, oh boy, this creates a whole new, kind of debate for us to talk about, but I don't know. I guess it's kind of, in the eyes of the beholder. Is 2.5% really low or not really low? I don't know. So it's a tough question. Well, I want to kind of define that. And what we're going to do here is this is called the alpha value, the alpha level. Okay? Sorry for my really bad handwriting. The alpha level is this symbol there, alpha. And I will tell you guys that most of the time the alpha level we use is 0.05 or 5%. Now, what this alpha level tells us is it's a cutoff, it's a threshold. Below 0.05 is rare. So anything below 5% would be considered rare. Anything above 5% would be considered not that rare, not that unusual, or not that crazy. So based on a p-value of 2.5%, that is lower than 0.05%, so we would consider this to be rare. Now, other times we might use a or an alpha value of 0.01, or we might even be really high and use an alpha level of 0.10. Now, I'm not going to discredit this, but remember, 10% is really high, so that would mean that 9% is rare. Well, come on, 9% is really not that rare. But sometimes we might use a alpha level of 10% if we don't want to be very strict. If we want to be very, very strict, we would go to a alpha level of 0.01. I'm not going to tell you what to use. Usually the problem on an AP test will tell you. It'll tell you the significance level, and that's their word for the alpha level. Another thing we call that is the significance level. And, usually, like I said, they'll give you a significance level of 0.05. What that is telling you is that below 0.05 means that you saw something significant. Above 0.05, you didn't see anything significant. Okay? Or if you want to go with a significance level of 0.01, that means anything below 0.01 or anything below 1% is considered significant. Anything above 1% would be considered not significant. So for our particular problem, if we stick with a 0.05 alpha level, we would in fact claim that 2.5% was significant. It was rare. Meaning that seeing this 80% was something special. It was something special. In fact, it was so special that we're going to go ahead and create our conclusion here that we're going to reject the null hypothesis. So this means that we do have significant evidence that the 74% is probably wrong and that the truth is actually higher. So the true proportion is higher than 74%. Now, couple things. We do not want to claim that the true proportion is now 80%. Remember, that was just one sample that showed 80%. But because of that one sample, and because of our p-value, we do have evidence that we think the truth is higher than 74. Does it mean it's 80? No. It just means that it's definitely higher than 74%. So again, let me kind of summarize that real quick. When you do see something significant, meaning your p-value is lower than alpha, and let me write this down over here. If your p-value is lower than alpha, that means you saw something significant. Okay? And when you see something significant, you will reject the null. You saw something special, right? You saw something happen that wasn't supposed to happen, but guess what? It did. Now, the opposite of that is if your p-value is greater than alpha, and this means you were not significant. And when you're not significant, it means that you saw something, nothing special happen, so you fail to reject the null. Basically, that's saying that what you saw was not that far away from expected, and it was nothing special, so failed to reject the null hypothesis. So hopefully that makes a lot of sense there, hopefully. Okay, so let's take a look at another example here, and this one it's so nice because I like this example because it's very clear cut. In the 1950s, 40% of high school graduates went to college. A more recent study revealed that out of 580 randomly selected graduates, 360 have gone on to college. So has the 1950s percentage changed? Okay, so here we go. Step one, we need our null hypothesis and our alternative hypothesis. The null would be that the true proportion is still 40% that we saw back in the 1950s. And the alternative, now notice when you read this, it never said did it increase, did it decrease, it just says has it changed. So a change could be good, a change could be not good or bad, but change could be higher or lower. So I'm just going to say not equal to 0.40. And I'm going to show you a little bit later on how that changes the problem ever so slightly. Okay, the second step was we still need our conditions. So very quickly, we'll just kind of run through them real quick. The 580 needs to be random. It did say that. It needs to be less than 10% of all college or high school graduates, and I'm pretty sure it is. And we do have 360 successes, and doing some simple subtraction, that would be 220 failures. So definitely both more than the 10, more than 10 successes and failures. Now for our work. Remember, our work is all to find that very elusive p-value. So here we go. The first thing I need is the truth. I was told that it was 40%, and that means I'm going to create a standard deviation for my sampling distribution. And again, standard deviation is because the standard deviation is based on the truth, and I'm assuming the truth is 40%. So square root of 0.4 times 0.6 divided by 580. and I get a standard deviation of 0.0203. So again, if it helps to kind of think about a sampling distribution here that represents many, many samples, we expect every sample to come back near 40%, but they might vary a little bit, and they'll vary a little bit by our standard deviation here of 42%, 44%. That's not special. 38%, 36%, all totally normal. Now, where do we fall? Well, I want to figure out a z-score for my, well, I guess I kind of got a little ahead of myself there. I need to find a z-score for my sample. Well, let's see, what was my sample? My sample was 360 out of 580. So what is that? 360 out of 580 is about 62%. Actually, I should use 4 decimals here since it's not exact. 0.6207. And I'm thinking, whoa, that's pretty high. Well, how high is it? Is that high, but still in the realm of it's okay, or is that like really, really high? Well, to do that, let's find the z-score. So here's the observed statistic, 0.6207, minus I was expecting to see 40% that I thought was true from back in the 1950s, and divided by 0.0203. And I get 0.6207 minus 0.40 divided by 0.0203. And I get, and this is the kicker, I get a z-score of 10.8719. And I'm pretty sure that everyone would agree with me that that was rare, that was special, that is significantly high, right? Now, I still need to calculate that p-value, even though I think we all hopefully know the answer. The p-value is going to be looking higher than this. I'm going to do my normal CDF, and I'm going to look more extreme. Remember, the p-value is the probability of the observed statistic, or more extreme, or higher in our case here. So I'm going to do a normal CDF of that value to 99, and I get, this is, it's not even worth me writing down, but it is 0.00000000000. There's 27 zeros all the way, and then there's an 8. So basically, I'm just going to put approximately 0. Okay, the p-value is so unbelievably low, which means that what I saw was very significant, okay? And now the great thing about this is I don't care what your alpha level is. You might use an alpha level of 0.05. You might even use an alpha level of 0.01. You can even use an alpha level of 0.005, and it wouldn't matter. Our p-value is so low that what we saw is very significant. So let me describe what that p-value means again. It means that there is approximately a 0% chance of seeing an observed value of 62% or higher when the truth, we thought at least, was 40%. So it's like, given that the truth is 40%, right? Given that we thought it was 40%, the probability of seeing 62% or higher is like impossible. But guess what? It happened. So what does that tell me to do? Well, it tells me to do the only natural thing I can think to do. Reject the null, right? Obviously, there's no doubt here. I'm going to reject the null. I'm going to go with the alternative, and that is that the proportion of kids that go on to college is certainly different than 40%. Now, because our alternative was just different than 40%, we don't want to claim it's higher. We don't want to claim it's lower. Obviously, we're pretty sure it's higher, but we just want to claim that it's different. Now, the other thing that I wanted to tell you about, because of this, because we chose the not equal to sign, what you do is whatever you get for your p-value right here, you times it by 2. You double it, because basically it's called a two-tail test. We're going to look at the extreme tail on the top and the extreme tail on the bottom. Well, the good thing is because of symmetry, they're the same, so you just times it by 2. Now, in our case here, go ahead and times 0 by 2. You're still going to get 0. It's not going to really change anything. But in later examples we'll see in class, sometimes that might make a difference. So anytime that you go with the not equal to sign, you simply find your p-value, as we've talked about, and then double it. So we'll start doing some examples in class, and hopefully hypothesis tests make a little bit more sense now to you guys, and that you understand the 4 steps, and then the most important is finding that p-value and determining what it means.